Welcome to the Explainer. So, have you ever really thought about why a planet can just keep orbiting the sun for, billions of years, but a bouncing ball loses its oomph in just a few seconds? It almost feels like some things have this endless supply of energy, while for others, it just vanishes. Today, we're going to figure out where that lost energy actually goes.
Okay, so let's really get into this. Picture it. A planet just coasting in its orbit around a star, and it's been doing this for an almost unimaginable amount of time. Now, think about a super bouncy ball. You drop it, it goes high, then a little lower, and pretty soon it's just sitting there. What is the deal? Why does one motion seem to last forever while the other just fizzles out?
The answer to this puzzle isn't really about the objects themselves. It has nothing to do with the planet being big or the ball being rubber. Nope. It's all about the forces that are acting on them. And once you get a handle on these forces, you unlock one of the most powerful ideas in all of physics. So it turns out we can basically sort every single force in the universe into one of two buckets. We call them conservative forces and non-conservative forces. And the main difference between them, the thing that really matters, boils down to a simple question. Does the journey matter or only the destination? This whole idea is called path independence. And trust me, it changes everything.
Right, so here's the crucial point. For a conservative force, the only things that matter are where you start and where you end up. In physics, when a force transfers energy, we call that work. And for these conservative forces, taking the long, winding, scenic route costs the exact same amount of work as taking a direct, straight shot. And this is just a perfect illustration of what I'm talking about. Look at this projectile flying through the air. Now, gravity is pulling on it the entire time, right? But if we want to calculate the work that gravity does, we don't need to worry about that whole beautiful arc. All we care about is the vertical change in height, that h. Gravity, our classic conservative force, it just doesn't care about the journey. It's all about the destination. But then you've got forces like friction, a non-conservative force, and it is the complete opposite. With friction, it is all about the journey. I mean, think about it. If you slide a heavy box across the floor, the longer the path you take, the more you're going to feel that friction fighting you, and the more energy just gets drained away, usually turning into heat. That energy is basically ripped out of your system, and you're not getting it back to do anything useful. So, okay, what's the big deal? One depends on the path, one doesn't. Why does that matter so much? Well, this whole path independence thing gives conservative forces a really unique and incredibly useful superpower. And here it is. This is the big one. It's the ability to store energy. We call this potential energy, and it is a superpower that only conservative forces have. I mean, think about it. When you lift a ball up, gravity lets you store energy in its height. A spring can store energy when you squish it, but friction, air resistance, nah. They can't store energy. All they do is take it away. Now, this superpower leads us right to one of the most beautiful and powerful shortcuts in all of physics, the law of conservation of mechanical energy. So if you look at a system and you realize, hey, the only forces doing work here are conservative ones, like gravity or springs, then you know for a fact that the total mechanical energy is going to stay constant. That's a mix of potential energy, which is the stored energy we call U, and kinetic energy, the energy of motion we call K. The energy can slosh back and forth between stored and motion, but the total amount, it never, ever changes. Okay, that equation is fantastic for simple stuff. But what happens when things get messy? What if you've got springs and gravity and maybe even a little bit of friction all at the same time? How on earth do physicists keep track of all that energy without their heads exploding?
Well, they use a visual tool that is surprisingly effective and, as you can see from this quote, kind of beloved. Now, officially, they're called energy bar charts, but pretty much everyone calls them by their much, much better name, LOL diagrams. And yeah, it's because they literally look like the letters LOL.
Think of it like a really simple accounting ledger, but for energy. That first L is just a bar graph that shows all the kinds of energy you're starting with. The second L shows what you end up with. And that O in the middle, that's where you define your system. Like, what objects are we actually talking about? Any arrows that go into or out of that O represent energy being added or maybe taken away by some outside force, like our old friend friction. So building one is this really logical process that kind of forces you to think through all the physics before you even touch an equation. First, what's in your system? Okay, what kind of energy does it have at the beginning? Is anything messing with it from the outside? And what does the energy picture look like when it's all over? It just helps you organize your entire thought process. And that's really the magic of it. Once you've drawn a good LOL diagram, turning that picture into the right equation is, well, it's easy. The hard part, the actual physics thinking, you've already done it. You've basically created a visual story of what's happening to the energy, and that makes the algebra that comes next way more straightforward. All right, so let's bring all this back around to our original question and see how these ideas actually give us a really complete answer.
And there it is. We've solved the mystery. The bouncing ball stops because non-conservative forces, things like air resistance and the energy loss during the impact, are constantly draining away its mechanical energy. The planet keeps going because gravity is conservative, and out there in the near vacuum of space, there's basically nothing around to steal its energy. So you see, this one little distinction unlocks the incredible power of energy conservation, and cool tools like LOL diagrams let us track that energy no matter how complicated the problem gets.
So this leaves us with one last kind of fascinating question to chew on. We've been saying that non-conservative forces make energy get lost from a system. But wait a minute, the first law of thermodynamics says energy can't be created or destroyed. So where does it really go? Something to think about. Thanks for watching.